Is quantum mechanics truly random? Is quantum mechanics as we currently write it down simply incomplete, in the sense that, say, classical statistical mechanics is incomplete? Statistical mechanics discusses the most likely outcomes based on, for example, the collisions of atoms or molecules in a gas. That in turn leads us, for example, to relations between pressure and temperature in gases. In a classical world, though, we presume that there is an underlying deterministic theory of colliding mechanical particles, which we could use if we wanted to. If we only use statistical mechanics, these underlying variables, which are the actual positions and momenta of each atom or molecule, are hidden from us in practice. Classically, however, we do presume that these actual positions and momenta do exist. Perhaps quantum mechanics has such hidden variables. If we could figure out what they were, the apparent randomness of quantum mechanics would disappear. Einstein, Podolsky, and Rosen came up with a famous thought experiment that they believed demonstrated the absurdity of the quantum mechanical randomness that's apparently involved in the collapse of the wave function. Hence, they were arguing that there should in fact be some hidden variables behind this behavior. This thought experiment has been known ever since then as the EPR paradox.
We can create two distinguishable particles, an EPR pair, that's EPR for Einstein, Podolsky, and Rosen, in a quantum mechanical superposition state of the form of one of the Bell states. For example, for two photons 1 and 2 going in different directions, we could create them in a state like this one, which is one of our Bell states. Such a state is a linear superposition of the state where the two photons are both horizontally polarized and the state where the two photons are both vertically polarized. In this state, if one measures one of the photons in a state H, that is horizontally polarized, according to quantum mechanics, the state of both particles is forced to collapse into the one element where we have photon 1 being horizontally polarized and photon 2 being horizontally polarized. And a measurement on the other photon is now bound to give the result H, horizontal polarization also. In this state, similarly, measuring the result V for one photon will lead, according to quantum mechanics, to the inescapable conclusion that the other photon will also be vertically polarized.
According to quantum mechanics, neither photon has a defined polarization until it's measured. So one is forced to conclude that somehow the measurement of one photon leads to a change in the other one's state. This is indeed a bizarre notion, especially if one arranges that the photons are very widely separated at the time that either of them is measured. Then there might be no possibility, during the time of both measurements, that any signal can be conveyed, even at the velocity of light, between the two measurement apparatuses. Einstein referred to such a change in state of the other particle as spooky action at a distance. He considered such behavior very strong evidence that in fact there should be hidden variables. For example, we might think that perhaps each photon actually does have a specific polarization at the time it leaves the apparatus, but we merely are unaware of it until the measurement takes place. Such a definite polarization would be a hidden variable. This polarization information would presumably be carried with the photon as a local property of the photon, hence being what is called a local hidden variable. Einstein apparently believed for the rest of his life that there should be some kind of local hidden variables. There was, however, apparently no experimental test that could answer the question as to whether local hidden variables actually existed. Local hidden variables would restore the belief that, though we do not yet have a theory that explains exactly how such variables behave, the world actually does agree with what we could call our local determinate view. In that view, we like to believe that things have actual well-defined states given by properties that exist in some region of space near the things. In 1964, however, John Bell proposed a way of distinguishing experimentally between local hidden variable theories and the predictions of quantum mechanics. This proposal, and the experiments that followed from it, led to a major change in the way that we have to think about reality.